Rest of the thermochemistry chapter, chapter 6 in the book today. Last time we were using enthalpy values to calculate heat in thermochemical equations, and so we looked at ways that you could manipulate those equations. That is, you could reverse the equations, and all you would have to do is just reverse the sign of the enthalpy. You could multiply an equation by a coefficient, either 1/2 or 2 or whatever you wanted to multiply it by, and you would do that to the enthalpy as well in that process. We also talked about how you could calculate enthalpies using calorimetry, that is, looking at temperature changes inside a calorimeter and knowing something about the substance that's present and the solution that you've put it in. And that would mean knowing the heat capacity of either the calorimeter or of the solvent that you put it in, which if it is a bomb calorimeter, that will be whatever the heat capacity is of the bomb. And if it was a coffee cup calorimeter, generally we would use water as the solvent, okay? The last topic that we are going to cover in this chapter has to do with using enthalpy equations to calculate the overall energy of a given reaction. Now, what you should remember, what I've been saying about energy throughout this chapter, is that we're really only concerned about final and initial changes, really nothing that's going on in the middle, okay? So what that means is that if we want to calculate, let's say, the energy of a reaction, like shown here, where I'm taking this compound and decomposing it into these three substances, and I want to know what is the enthalpy of that reaction, I may not be able to do that given reaction in a calorimeter. It may be too difficult. It may be a substance that just explodes, okay, and so it gives off way too much heat. So you may not be able to do it in one step, is what I'm getting at. But that doesn't mean that you can't look at a series of reactions that might lead to that same overall process. In other words, if I gave you information about, let's say, reactants and products in the top equation, that there may be a way to take these equations on the bottom and manipulate them to get the equation on the top, okay? What allows me to do this is by using what is called Hess's law, okay? Hess's law. This is what is known as the indirect method. To calculate enthalpy. The indirect method to calculate enthalpy. That is, as enthalpy is a state function and only depends on initial and final conditions, we can use a series of chemical reactions, or a series of thermochemical reactions, we can use a series of thermochemical reactions to calculate the overall enthalpy of a given reaction. Okay? Now, even though the reactions may not look exactly like what I've got on the top, there are ways to manipulate them, okay? And so there are several ways to approach these problems, but here are some general guidelines, okay? So this is not what you have to do, but this is my general thinking when I go in to solve one of these problems. First of all, find your reactants, okay? Find your reactants wherever they are, reactants being on the things generally on this side of a reaction arrow. They need to match up perfectly. States of matter and the number, okay? So here we've got NOCl gas. Is there an equation that has that in it somewhere?
Yeah.
Where?
The second one.
Okay, so right away, one of the things that would really help me is if I numbered those equations so that I could know which one is which. So I'm going to call this one equation 1 and this one equation 2. I like that better than the top one or the middle one. That just seems better, okay? So if that's equation number 1, this is the delta H for number 1. Everybody follow that? And if this is equation 2, this is the delta H for equation 2. Okay? All right, so first you're going to need to find your reactants, okay? Then what you want to do is manipulate that equation so that it matches. So that it matches the reaction in question. Okay, so what I mean by that is NOCl is on the wrong side of that equation in number 2. Does everybody see that? Okay, so how could I move it to the other side?
Flip it.
So I could reverse it. We've done this before, right? We reversed it. All right? And do I have the right number?
No.
No. So does everybody see that I have 2 of these and I only have 1 of these down here? Okay? So what do I need to do?
Multiply by 2.
Multiply it by 2 and reverse it. So that's what I'm going to do. So I'm going to reverse equation 2 and multiply by 2. I'm going to reverse equation 2 and multiply by 2. All right? So that means I've now got 2 NOCl gas, and that is now going to 2 NO gas plus 1/2 times 2, that's 1 Cl2 gas. And so if I did it to the equation, I have to do it to the enthalpy also. So I reversed it, and I multiplied it by 2. Okay? I will plug the numbers in at the end. Okay? Does everyone see what I did? How I did this? Why I did that? Okay? Now, once you've done your reactants, then you want to go for your products. Okay? Do the same for products. And add the equations together. Okay? All right, so where are the products?
Before you reverse it or after?
Well, what do we have here? This is the equation that I'm solving for, right?
Mm-hmm.
I've got the correct number of NOCl, right, on that side, okay? What about my products? Well, I'm good on chlorine, but what about O2 and nitrogen? Where are they at?
The first.
Yeah, they're right here, right?
Yeah.
Okay. But what's wrong with those?
There's only half of them.
There's half of them, and they're on the wrong side. So what should I do there?
And times it by half.
Times it by
4.
About 2.
by 2. Does everybody see that?
No.
So if I multiply 1/2 by 2, I get 1. Right? I got one of these.
For the equation that you reversed, why is it negative 2 right there?
Well, if you reverse this, you always reverse the enthalpy.
So wouldn't it be positive 3?
It is. I'll do that in a minute.
So why'd you put negative 2?
I'm going to do that in a minute.
I'm confused.
Well, I can either leave it like this, or I could plug in right now for what that value is, which would be what? Negative 38.6.
So you're just multiplying it.
I'm just gonna do it later though. Okay, if you do it in the process of, like if you do it in each step, you can do it that way, but I recommend leaving it in its algebraic form first.
I didn't know if you were like writing it as that, or if you like you were multiplying it. I didn't know if I was confused.
No, I'm multiplying it by -2, and as you said, that's gonna make it a positive. Okay, so I am doing that. I'm doubling it, and I'm taking the negative of it. Okay. All right. So what I need to do on the first equation. So what I need to do there is I need to reverse equation 1, right? So that I get the N2 and the O2 on the product side, and what? Multiply by 2. Okay, so what do you get when you do that? Two NO gas goes to N2 gas plus O2 gas. And what did I do to the delta H?
Times by 2.
And?
I reverse the sign.
No, okay. All right. Okay, so I've done everything I need to do. Now I need to take the two equations and add them together, okay? So if I do that, if I bring that equation over here, I've got 2NO gas goes to N2 gas plus O2 gas, and my enthalpy there is -2 delta H1. Now I need to take this and add these two things together. Okay, so what does that give me? I've got 2NOCl gas plus 2NO gas goes to 2NO gas plus Cl2 gas plus N2 gas plus O2 gas. And I need to add those two things together. So that's going to be -2 times the sum of delta H2 plus delta H1. Okay, so I just made it easy to put those numbers in your calculator and hit enter.
You knew to start with equation 2 because the 2 NOCl was on the second.
Yeah, I just move, I make my way from left to
Left to
right,
right, okay.
basically is all I'm doing. Like I'm like, okay, where's this guy, where's this guy, where's this guy, where's this guy? Once I've got all those accounted for, I add the equations together, okay? Now you may be like, but there's some extra junk in there? Like what about NO? I don't see that in this equation.
Don't worry about it, did it?
When you're adding those together, could you just cancel out the 2 NO gases, like, and not even write that in?
You can, but you should see they have to be exactly the same, okay? Like, do you guys remember when we did spectator ions? This is very similar to that, okay? So in other words, if I've got two of the same exact thing on both sides of the equation, same state, same everything, can I cancel those out? Yeah, they're not really part of the reaction, are they? So you can basically just cancel those things out. Here and here. And what do I have left over? Now I have that equation. So now all I have to do to solve for the enthalpy is to plug the numbers into this right here. You could either have done it as you were going along and adding them together, that's fine, or, like the way I like to do it, is do them all at once at the end. So this is going to be -2 times the sum of delta H2, which is -38.6, and delta H1, which is 90.3.
And so on a test, like, are you looking for that whole thing, or are you just looking for like the numeral part?
I'm looking for the numeral part, but you should think about the equations.
Okay.
Because if you skip one of those steps, I won't know where the number came from. Okay?
So done correctly, like given to us?
Exactly.
So we can check ourselves? based on
Yes.
that? Okay.
Yes, if they don't match exactly states and coefficients, you haven't done something right. Okay? All right, so what's that turn out to be?
Negative 103.4.
Okay. All right, does that make sense how we did that? All right. Okay, I want you guys to do this one on your own, okay? So two pollutants from car exhaust are carbon monoxide and nitrogen monoxide, NO and CO gas. They can be reacted together to form carbon dioxide and nitrogen gas. That's something that your catalytic converter can take care of, okay? Given the following thermochemical equations, calculate the heat of the reaction above. So using those two equations on the bottom, calculate the equation on the top. Again, you've got N2 gas plus O2 gas goes to 2NO gas, and the bottom one is CO gas plus 1/2 O2 gas goes to CO2 gas. Okay? Okay, so I gotta get something from my office. You try that out. Okay? I'll be back.
Oh, so we gotta reverse the thing.
Okay.
Okay, that makes sense, so you just flip it.
You gotta reverse it and then you gotta multiply it by 1/2.
Obviously, you just flip it, that'd be fine.
Okay.
Okay. I don't know which one you pick to do first.
Pick from left to right. Start with NO.
Oh, okay. So we do one, okay, so 2NO yields N2 equals L2,
I don't know, the first one we reversed it, so I'm doing some.
and then so one be positive, one be negative for the delta H values?
Yeah. And
That's about where I'm at. so, I don't know right now. I'm just putting my numbers, so I look intelligent.
The second one stays the same, right? With that one, just the first one, that one.
Where the hell does 90.3 come from?
I have a question.
Yeah, we can do that.
So you would flip the second one and multiply it by 2, right?
Flip the second one, multiply it. Why are you multiplying it by 2?
Well,
Can't you just leave it? Yeah, you can. Just leave it.
I mean, the reason why I'm asking is that this equation, you see there's a CO here, and this is the only equation that has CO in it. And is it on the correct side?
so could you, so the top equation, could you divide the top equation by 2?
You don't want to do anything to the top
Then
equation.
how are you gonna get it half?
Have faith, because it's going to work itself out if you did it right.
The first one.
Yeah, like they should work themselves out, because that's something I'm going to tell you about these, is I'm not going to give you a dummy one. Like, I'm not going to give you like, oh, a bogus equation that you don't need. You'll need to use all the equations that are given to solve it, okay?
Well, how are you gonna get half into? Like,
Well, let's do it.
Don't understand.
All right, let's do it. Okay, so we'll just start with the second equation, all right? So what I'm seeing right now is if we're starting on our reactants, I've got one CO here, it's on the correct side, and I got one CO there, and they're the correct state and the correct number. So I just need to use equation 2. All right, so just use it. Don't do anything to it. So just write it down. So you've got CO gas plus 1/2 O2 gas goes to CO2 gas. And that I'm just going to call, this is number 1, this is number 2. I'm going to call this number 1, I'm going to call this number 2. So I'm not doing anything to that delta H value. Not multiplying it, not doing the inverse.
I found it easier to do it how you told us to do it the first way, which is to start with the very first thing you see.
Well, I mean, we get there the same way.
Okay.
Same difference.
I think because you were just saying you're confused about the second one not using it, because the first one, if you do it with the first one, you
No,
can
I'm
see.
confused because whenever I look at it, I see the first one, and then I look at the equation at the top, and I see half into, and then there's in the first one. there's
Yeah, but only
into.
worry about what's going on over here. Worry about this part later, okay? Just worry about what the reactants. So we can start with say, oh, there's the CO, that's a reactant. I didn't tell you which reactant to start with, so it doesn't really matter. So, okay, we'll do this one, there's that one. Okay, what's the other reactant?
NO, but there's nothing. Well, the NO's on the other side.
So it's in equation 1, but it's on the other side, and there's 2 of them.
So you gotta flip it.
And
divide
by,
two.
okay, that's it.
Okay, I understand. You
What?
told me that we don't divide by 2.
When did I say, you said that about the second equation.
Oh, no, I was saying that.
Okay, well, no,
It
yeah,
has-
okay, so that's why I'm asking you to go walk through your thought process.
Because now we're gonna get half into, because when we flip it.
Well, let's do it. Okay, so so does everybody agree with that? You take the first equation, reverse it, and divide by 2. Okay, so, and why did I do that? Because I want to get the correct number of NO on both sides, okay? So there's the NO, NO. So equation 1, reverse, and multiply by 1/2, okay? So that's going to be NO, gas, goes to 1/2 into gas, plus 1/2 O2 gas. And so what did I do to my delta H1? I took the negative of it, reversed it, multiplied it by 1/2. Okay? Now let's look at our product. Okay? So we've got our CO, we got our NO, that's looking good. What about the 1/2 N2?
Yeah.
Is that on the correct side? Is it in the correct state?
Yes.
Okay, that's good. What about the CO2? Correct side, correct state. All right, so everything is accounted for now, all right? And I think, as you can see, if you added the two equations together, what would happen? Does everybody see there's a 1/2 O2 here and a 1/2 O2 on this side? Right? They're same state, same everything. Those cancel out. So this is going to be CO gas plus NO gas goes to CO2 gas plus 1/2 N2 gas. And that's delta H2 minus 1/2 delta H1. Everybody follow that? How I got that? Okay, now just plug the numbers in. Delta H2 is minus 283 kilojoules minus 1/2 times delta H1, which is 180.6. Okay, so what do we get when we add that together? Minus 373.3 kilojoules. Okay, does that make sense? How I did that, what you have to go through to think about that? Okay. And like I said, I'm not going to give you one where it won't work itself out, okay? Everything will cancel out at the end. And if I give you 3 equations, you're going to need to use all 3 equations, okay? So make for sure, I'm not going to give you a dummy one, okay? You're going to need to use all the thermochemical equations given to solve for the reaction, whatever it is. Does anybody know anything about this process right here? This was in the news about 2 years ago, about nitrogen waste. Yeah, but there's something about as a car pollutant.
Carbon monoxide?
No, the nitrogen waste
Oh, nitrogen.
specifically. Anybody own a Volkswagen?
Volkswagen diesel problems.
Yeah, well, not their diesel problems, more about their lying about their vehicles problem. Have you heard this story? Okay, so in Germany, well, there was a report that came out 2 years ago that German automaker Volkswagen claimed that their vehicle had phenomenal emissions tests, and it was not producing really as much waste as they claimed that people were claiming that it does. And they were saying, oh yeah, we burn clean diesel, everything works good, we're not producing any waste. Well, what they found out is what their vehicles do is when you go in for testing and you plug the vehicle in, the vehicle recognizes that it's being tested and it switches on a little mechanism that makes it seem like that the car is producing less nitrogen waste than it actually is. So it's basically set up to fool the people for the emissions test, okay? And so when they were confronted about that, they were like, yeah, we did that. So they totally owned it, okay? And so it was like, yeah, we thought we'd make a lot of money doing it, and we did. So if you owned a Volkswagen and you took it in last year, did you do this? Did you get did you get the discount? There was a professor here in the English department, Professor Neifert. He actually took his vehicle back to the Volkswagen over at Onion Creek, and they gave him like a credit to buy a brand new Volkswagen, okay? Because of this recall that they had to do as a result of this thing that was going on. And this reaction shows you that if you don't deal with this nitrogen waste, because what they were saying is the nitrogen waste is what was being hidden, and you produce nitrogen waste when you combust fossil fuels, okay? And they were not being honest about it, okay? So that was something that was in the news recently about this. Okay, now the third question is related to this, but it's a little more complicated, and I want to introduce an idea with you. So, have we talked about the tables in the back of the book at all? Did I mention anything about those yet? Okay, well, one of the things that you will notice in this chapter is you will oftentimes see delta H values given, and sometimes you'll see delta H with a little degree symbol above it, okay, with that O. Now, that's something I want to mention about. Whenever you see this right here, this is referring to something that we call standard states. Okay? Standard states. Meaning there are values that you can look up in the back of the book that tell you how much enthalpy is associated with the generation of that molecule from its elements, okay, under these standard state conditions. That is, all solutions are run at 1 molar concentration. All of them are at 298 Kelvin when they ran these experiments. And they are also at 1 atmosphere of pressure. So then whenever you see that little degree symbol, it's saying, oh, those are standard state conditions that they ran those experiments under using these conditions. If you do not see the little degree symbol here, this is something that is non-standard state. Meaning these things do not apply, okay? Meaning it may not be at 1 molar, it may not be at 298, and it may not be at 1 atmosphere conditions. So that's an important distinction, okay? Tables in the appendix, back of book, will list delta H0 values for various compounds. These values come from making 1 mole of the substance, come from making 1 mole of the substance from its elements in their most stable forms. This is often referred to as the heat of formation. And sometimes, just to emphasize it, they will put a little F underneath the delta H to indicate, oh, that we're talking about that substance being formed from its elements. Okay? So if you went to the back of the book right now and you looked up the heat of formation for water, okay, what would you find for that value? Well, first of all, is that enough information to go look that up? Could I say, oh, I want to find the heat of formation of water, I'm going to go look it up in the back of the book?
Yes.
Yeah.
Because it's a standard state.
Yes, but you've got to know what form the water is in. So is it a solid, is it a liquid, or a gas? So there'll be 3 values in the back, 1 for each, okay? So you've got to know, well, am I talking about water being formed as a gas? Am I talking about water being formed as a liquid? Am I talking about water being formed as a solid, okay? Now, what's water being formed from? What elements makes it up?
Hydrogen.
oxygen.
Okay, so we're talking about H2 plus O2 is making H2O. Now, that equation is not balanced, okay? But I want to make 1 mole of water, so I can't change that number right there, okay? So what would I need to do to balance this equation?
Half of oxygen.
Yes. Is that okay to do that?
It's the only way you can keep H2O as one, so.
Well, but again, what quantities are we talking about here? Are we talking about molecules or are we talking about moles? Can I have half a mole of something?
Yes.
Yeah, so I'm not talking about having half a molecule of oxygen, I'm talking about having half a mole of oxygen. Okay, so remember when I went back and I said, you'll see fractional coefficients in this chapter, don't let it bother you, because we're talking about mole quantities, okay? So if you went and looked this up in the appendix, you would see that the heat of formation of water as a gas from its elements is minus 241.82 kilojoules, okay? So that is what that's telling you. This is the amount of heat that's released whenever you take a hydrogen and oxygen gas and react them together. Okay? Now, if we're talking about elements in their most stable form, well then that's saying that those elements are basically kind of like a baseline. So elements in their most stable form will have a heat of formation of 0. Okay? In other words, if you went up and you looked in the back of the book for the heat of formation of hydrogen gas or oxygen gas, those values would be 0. Okay? So that's something you should know. And for all elements, the heat of formation is 0 in their most stable form. Okay? Bless you. For chemical reactions, and again, these are for chemical reactions given, we can calculate the heat of form, or the heat of reaction. We can calculate the heat of reaction from standard state conditions we can calculate the heat of reaction from standard state conditions if we subtract products or reactants, heats of reactants from heats of products. In other words, to calculate the overall heat of a reaction, all you have to do is take out whatever the heat of your product is, that's what you end up with, that's like your final, and subtract whatever the heat is of your reactants. That's your initial. And the difference should be the heat that's either needed or given off. Is it exothermic? Is it endothermic? Okay? Now, obviously, I don't expect you to memorize any table data, and if I give you a question like this, I will give you the standard state values, but you've got to know how to use them. Okay? So, with that said, let's look at this last equation. So I want to calculate the delta H0 value for the reaction below, given the following data. So you're told what the heat of formation of CO2 gas is, what the heat of formation of water is, and what the heat of formation of a methanol is. Okay? And you're not given the heat of formation of O2. Why not? What is the heat of formation of O2 gas?
0.
That's why it's not given. Okay? So you should know that. Okay? All right. So all I have to do to calculate the heat of this reaction right here, in other words, I want to know what is this, is all I have to do is add up the product heat and subtract that from the reactant. Okay? But that means paying attention to how much you have of each thing. Okay? So what do we have as far as products go? We've got CO2, gas, and what else?
Water.
How many waters?
2 moles.
2. So what do I need to do?
Times 2.
Okay, so you're going to take whatever that is for water and multiply it by 2. Okay, so there's my products. All right, and I'm going to subtract that from my reactants. All right, so what are my reactants? I've got CH3OH liquid, one of them, and I've got 3/2 O2. Okay. Now just fill in the blank. The heat of formation of CO2 is minus 393.5. The heat of formation of water is minus 241.8. The heat of formation of methanol is minus 238.6. And then 3/2 times the O2, which is 0. Okay, does that make sense how I did that, where all the numbers came from, what's going on there?
Is that always gonna work out that nicely where it's like in order of how you plug it in?
Well, it's always going to be products minus reactants.
Yeah.
I mean, I
like-
can't guarantee the list will line up like that,
that's
but
what
you
I'm
should be
saying.
able to like
So-
match them,
Yeah.
okay? Regardless of how they're listed below it, okay? Does everybody see why I multiplied by 2 and 3/2, where that came from? Okay. All right, so what can you say about this reaction? What's the heat of this reaction overall?
Negative 399.9.
Kilojoules. Is that what everybody got when they did this? Okay, that is not what I got.
No.
I got negative 638.
That's what I got. And I think maybe you didn't multiply this by 2, and those you add those two numbers together. Okay? Is this exothermic, this reaction, or is it endothermic? How do we know?
Because it's a negative.
So that means it's exothermic. It means it gives off heat, okay? Because what that's saying is that I have less energy total for products than I have reactants. So where did the extra energy go? Off to the surroundings, okay? So that's why if you get a negative value, that's an exothermic reaction. That's heat that's given off. If it's a positive value, well, that means that's extra heat you've got to put into it in order to get it to react.
So when you ask this question, you're always gonna give us those numbers, and then if you don't, it's basically zero. Like you're not gonna make us like how it has O2. Like what if, let's say, like we didn't know that it was zero.
You got to know that's zero, though.
Yeah, but so if you didn't list it, wouldn't it be zero? Because you would always list the numbers.
Well, I mean, you can look at it like that, but I'm kind of like, you're supposed to infer, like, kind of like what you're thinking, like, well, why didn't he list oxygen, right? Well, because it's zero, because it's an element. So, I mean, that's one way to look at it, but you should just remember also that an element's heat of formation is zero, okay? So I shouldn't have to give you that one, okay? Does this make sense, guys? All right? Because we're getting ready to shift gears again, okay? One more time. This will be on this test. So you need to know how to do Hess's law, thermochemical equations, all the stuff in this chapter that we've talked about. Okay? Because we're going to see energy values used when we get started talking about electrons. And so this is kind of the last chapter that we're going to be dealing with that deals with these type of macroscopic properties. That is, these are like things that you're weighing out. We're talking about quantities in the lab. These are experiments that you could run. We're going to start getting really theoretical now, okay? Talking about concepts that we are still kind of fuzzy on that you may not think you're fuzzy on. So before I introduce that, how would you define an atom? Coming out of this class right now, what would you say an atom is?
Almost unit of an element.
Okay. Is there anything an atom has that's unique about itself that maybe differentiates it from other atoms?
It's electrons and
The structure of it.
Okay, so whatever, like the subatomic particles, right? The protons, neutrons, and electrons. Where are those located in the atom?
The nucleus and the orbital.
The nucleus, okay, that I buy. The nucleus is where's the nucleus?
The center of the atom, and the
What's in that? What is in the nucleus?
protons and neutrons.
Protons and
Electrons are
neutrons,
orbiting
right? And that's
the-
where like almost all the mass is, right? Where are the electrons?
Orbiting the neutron.
In the what? I haven't said. I didn't tell you, okay? I got glossed over that, all right? So you mentioned the word orbital, but what's an orbital?
I guess the outer rings of around the neutron.
Okay, so this is the nucleus, right? You got a positive charge. Then that means, okay, so is like the electron like circling that like that. I mean, that's what I'm asking.
Wouldn't it be like more random though? Like even
Well, is there anything wrong with this model? Let's first think about this, because this is actually a model that people suggested. I mean, everybody knows, at this point, everybody knew about the solar system, right? And how the planets go around the sun. This really feels good. Like, what if the little tiny atoms have like little electrons that go around their nucleus like a sun, right? Like that feels really right, okay? Is there any reason why this couldn't be the case?
Because like the isotopes are like with, or the charges that they have and sharing of electrons and stuff.
does it have to do with like reactions?
No, well, okay, here's my question is, what's keeping that electron in orbit? Okay, I mean, here's one thing, like, since these are opposite charges, I mean, why doesn't this just decay, crash into the nucleus and explode?
It's gotta be going with the time.
Yeah, so there's something like weird about it. Does everybody see that? Like, it can't be traveling like in a normal path, circling the nucleus because they have opposite charges, because it would have a decayed orbit and it would crash into the nucleus, and then we couldn't have matter as we understand it. Because we already know the atom is mostly empty space, and so what's the space? Everything between where the electrons are, and when I push on something, what am I pushing on? If I push on you, or I push on this board, or I push on this like eraser, why is that? Why is my hand not melting into the board? And like, because there's repulsion. Okay, I'm pushing on the electrons on that substance, and there's electrons in my hand, and we're pushing back, right? Well, that means that there's electrons are being kept in those orbits. They're not just squishing together and coming back out. Does everybody see what I'm saying? So right away, you should be suspicious about the physics that you've been taught, because this is the model that they present in high school, and there's nothing wrong with it, because you can say, well, if you've got two electrons in this orbit that goes around the nucleus, but you used the word orbital. So what is that?
Like every electron belongs in a certain orbital, or it's certain space, I guess. I don't know.
Like its region.
Yeah, like it's like designated region or designated space.
So each electron kind of has its own little
Home.
Little hum. Yeah, that's a good word, a little hum. Does everybody see where I'm going with that? Like electrons kind of have their own little home. But how many electrons live in a house?
I think it depends on which element you're talking about, or...
Well, do they all live in the same house? Does it make sense that I would have, like, let's say an element with 50 electrons? Would they all be in that same orbital?
The first orbital can only have 2.
Yeah, it's like every section.
Okay, so everybody's saying some rules, and you're right, what you just said. But this has to be unpackaged. Do you see what I'm saying? Like, why is it there's just 2? Why is there a certain house that they live in? How many houses are there? And how do you know at what point do you go further out? Okay, like you can't crowd them all together in this one little space, so how do you know when to grow it out? Have you ever wondered why the periodic table breaks in its periods? Like why it goes, there's 2 elements, and then it breaks and goes to the next row, and then there's 8, and then it breaks and goes to the next row? That's almost kind of like it's going to a new area, right? Like that's where it grows out to a new area. My reason for saying that is the periodic table shape, why metals or non-metals are where they are, and where those breaks occur in the table all come back to what I'm just now talking about. Now, there's a school of thought that thinks that this is the first chapter that I should have covered in this class, what I'm getting ready to tell you right now. I don't, okay? The reason why is because I think you need to know what a joule is. I think you need to know how to balance an equation. And I think you need to know a little bit about how to use things in the laboratory first, okay? Because what I'm getting ready to tell you now is mostly physics, okay? And how physics became chemistry, okay, over a certain period of time, and it kind of became its own field, okay? So this chapter, this is one of the only chapters that I'm going to do this, has a PowerPoint presentation, okay? And the reason why is because, well, there's just a lot of graphs in this chapter, okay? And there are a lot of illustrations. The math will kind of look a little bit crazy, but it's not that bad. Most of it is just multiplying numbers together and adding numbers up. So don't let the big exponents frighten you, okay? It's simply a matter of just multiplying and adding numbers together. Okay, so that being said, this is available on Blackboard, so you don't need to write every single thing down that I'm saying today, okay? You can go back and look at this at your leisure, but I will be going through this together. Now it says chapter 6, and I believe this is actually chapter 7, okay, in our book, and I will update that.
Is this on the test?
This will be on the test also, okay? Okay. All right, so what we're going to be talking about now is what is called the quantum model of an atom. And the goal of this chapter is to answer where are the electrons in an atom. That is really it in a nutshell. Okay? So, one of the things you need to understand is how small an electron is. Because we've gone through this, but you may not have recognized it when we were going through it initially. So, when we talk about how small an electron is, this is a statistic to take away. A single speck of dust, one speck of dust, has more electrons in it than the number of people who have ever lived on Earth. That means lived, died, the whole of humanity. I mean, how many billions of people that is. That is in a single speck of dust, okay? That is how many electrons are in matter. Okay, so the number is staggering, okay, when we think about it. One of the things we know about electrons is that if you understand how electrons behave, that is how an atom behaves as well. If I had to say what is the single most important concept in chemistry, it is understanding how electrons behave, okay? Chemistry really has to do with making bonds and breaking bonds. Now, all this stuff about moles and grams and stoichiometry, that is relevant, and you need to be able to understand how that works. But understanding that doesn't explain why a chemical reaction happens. It's just like you're just, oh yeah, okay, those react. Well, why do they react? Why do those electrons want to interact with other electrons with other elements in the first place? Why don't they just mind their own business, okay? And why are they getting into another element's business and interacting with them? Well, as you suspect, it has to do with stability. And another concept that is very difficult to grasp is that it has been shown that it is impossible to directly observe an electron in an atom as it is behaving. Now, I'm not saying that it's impossible to not view locations of electrons, but to actually see an electron in motion, this is something that cannot happen due to the size of the electron. Now, you may go, well, it shouldn't matter. If it's super small, we should be able to see it. But electrons don't travel in straight lines, okay? In fact, they don't even travel in arches or any kind of zigzag pattern. In fact, they warp, okay, from one area to another. And you can't travel the space in between. It's like they're in one location and then they're in another location, and it's like everything in the middle is not there. Literally like warping from the Star Trek Enterprise down to a planet, okay? So that is what we are talking about here. So whenever you hear the idea of quantum mechanics, it's talking about a type of physics that is not classical, okay? Like it has its own set of rules. So how in the world did this ever come about? Well, if you understand this model, it will explain the manner of how electrons exist and how they behave in an atom. When you get done with this chapter, here are some things you will be able to say. Why are some elements metals? Why are some elements non-metals? Why do some elements gain one electron to form an anion? And why do others gain two? I mean, we've all learned that, right, the elements in the first column of the periodic table tend to want to lose an electron to become a cation, to form a +1 charge. Why? Why do the elements that are like fluorine, chlorine, bromine, and iodine, the halogens, want to gain one? I mean, other than saying, well, some are metals and some are non-metals, that's all I've told you. Metals tend to like to lose, non-metals like to gain. Why? No one asked me, okay? You just believed me, okay? So there's a reason for those patterns, okay? And as you may suspect, the reason why the periodic table is called the periodic table is because patterns repeat periodically on it based on how many electrons an element has. Now, to understand all of this, we need to go back and review some fundamental things about the nature of light, okay? So one of the things you should know is that light is actually a type of radiation, okay? It's an electromagnetic field, all right? You have a magnetic field and you have an electric field that's associated with a light wave that are perpendicular to each other, okay? That means that light has a certain amount of energy associated with it, okay? If you were to measure the speed of light in a vacuum, it is a constant. It is 3 times 10 to the 8 meters per second and is given the symbol C. That is the same C that's in E is equal to mc squared. There is no speed faster than that. That is the universal speed limit, okay? One of the things that Einstein proved, okay, and that actually experiments were done later, is that as you approach the speed of light, time slows down. Think about that for a second. That tells you that any body that's in motion, they don't feel the full gravity of time, okay? If you are in motion, the time difference is different as opposed to bodies that are at rest. There was an experiment done in the 1970s where they put an atomic clock on an airplane and they flew that airplane all the way around the earth, okay? And it was at a constant speed of over about 500 miles per hour, okay? Now that's far from the speed of light. But since they did it for a 24-hour period, when they finished the flight and they got the clock, the time actually, they had gained time. And I don't mean time change, okay? I mean like they actually gained time by traveling at that speed for that long. Now it was a minuscule amount of time, but that is telling you something about how light travels and how it affects time. Did you know that a lot of the stars that you see outside, they're gone. Those stars don't exist anymore, okay? That's how far away those stars are, okay? Like they existed, gave off light, and are now gone, okay? So when we talk about space, you immediately start talking about time, okay? Those two things are related, okay? And it's really incredible if you start to think about it. And it's all related to the nature of how an electron behaves. Another thing you should know is that light travels at a much different speed as other forms of energy, okay? So for instance, when when I clap my hands, you hear that. And that may be like, okay, well that was instantaneous. But we're getting ready to have a thunderstorm pretty soon, okay? And what's the order of operations with that? When you have a lightning storm, you see the lightning first, you hear the thunder second, okay? And those are events that are occurring simultaneously, okay? So as soon as you see the lightning, it's like it's instant, okay? But you don't hear the thunder until later. That's because the speed of sound is moving much slower than the speed of light. If you go to a fireworks display, you will hear the pop after you see the light, all right? You'll see the light first, then you'll hear the explosion. That's because the speed of sound is about 340 meters per second, which is fast. That's hauling, okay? But the speed of light is just far faster than that, okay? So that's one of the things you need to see is that lights and color and that their speed is related to a much, much faster constant than other forms of energy. And guys, what have you done when you burned things in the lab? Does everything burn the same color? Why not?
Because you're not burning oxygen, you're burning something else.
Well, yeah, like what? So you're telling me if you put different elements in a flame, they burn different colors? Yes, that's right, okay? Elements burn different colors. Why? Aren't they all made of the same thing?
Different electrons?
Yeah, the electrons are in different locations, okay? See, here's one of the things you may want to be thinking about is where does light come from in the first place? Like if you heat up an incandescent bulb or any kind of bulb, the bulb in these rooms, okay? How is this producing light?
Gas.
What kind of gas? Do you know what's in all the fluorescent bulbs in here? Mercury, okay? They're all full of mercury. Like these bulbs are irradiated mercury. Like we're irradiating mercury, we're passing electricity over it, the mercury is getting hot, its electrons are getting excited, and then they are going back down in energy, and then when they do that, they give off this color light, okay? But if, let's say, it was filled with copper, would you get the same color light that would come out of it? No, because the electrons would be in different locations. Do you see what I'm getting at? Like this is like a fingerprint. This is a way to identify an element based on the color of light that it gives off. That's because even though that's the speed of light and it's constant, do all light waves have the same energy? No, they don't. So if you want to characterize waves, there's a couple of ways to do it. One is you have to think about its amplitude. That is, how tall is the wave? How big is it? Okay? So in general, when we think about this, waves that are tall versus waves that are small, tall waves have more energy than shallow waves, waves that aren't very tall. So the higher the amplitude, the brighter the light, so to speak. The other variable is wavelength, okay, which is given the symbol lambda, all right? This is the distance from one peak to the next of a wave, measuring that distance, okay? And it turns out that that distance that we measure, okay, it kind of varies, okay, between different types of waves. That distance does not have to be constant, nor does the brightness of a light have to be constant either. The other way we characterize light is by thinking about its frequency. Like since waves are in motion, how frequently do those pass through a given point in a second? That's defined as a hertz, okay? So how frequently does a beam of light, or a light in general, pass through a given point in a second? And so you guys, I mean, you can't really, radios are now like awesome the way they're set up. But in the good old days, there were some dials, right? And you would like turn the dial to get to this like particular frequency, okay? That's because radio waves, which are outside, we're being bombarded by those, by a particular, I don't know, radio tower that's sending out a frequency for us to pick up and tune in on our radios, okay? And so those frequencies have a particular energy that you can measure. It turns out that the energy in a wave is directly proportional to its height, how big it is, and what its frequency is. Now, here's the takeaway from that, okay? So, frequency. Which one of these two things do you think has more energy? This one? Or this one? Which one has more energy?
Second one.
The second one. Which one had higher frequency? Second one. Higher frequency, higher energy. Okay? That's the moral of that story. So the greater the frequency, the greater the energy of a wave. Mathematically, that can be calculated. Okay? In other words, we can say that the frequency of a wave is defined as the speed of light divided by what its wavelength is. Okay? That is, and I like this form of the equation better, lambda, which is wavelength, times nu, which is frequency, is equal to c, speed of light. What that's saying is that as your wavelength increases, like your wavelength gets longer, what happens to your frequency? Like if these two things multiplied together have to be equal to c,
Decreases.
if one of these gets bigger, this one has to get smaller. So as wavelength increases, well then frequency decreases. And what did I say about frequency? The greater the frequency, the greater the energy. So if you have less frequency, what does that mean about your energy?
Less energy.
Yeah. That's the relationship you need to conceptually understand. So wavelengths that have waves that have big wavelengths tend to have low energies. And the reverse is true. If the wavelengths are small, then the frequencies are larger. And the energies are larger as well. Okay? So that can be mathematically calculated easily with that equation, which I'll provide you on the test, and I'll tell you what the speed of light is. But you've got to make for sure you have everything in the correct unit. Meaning if C is meters per second, well, that means wavelength needs to be in meters, okay? And frequency needs to be in inverse seconds. So, how would we do that? How would we calculate the wavelength of red light given its frequency? So what variable am I solving for in this equation? This guy, all right? So what would that be? If I rewrote that equation, what would it?
Speed of light divided by frequency.
Okay. All right, so what would that be? So that would be 3.0 times 10 to the 8th meters per second. And then my frequency would be 4.62 times 10 to the 14th inverse seconds. So does everybody see the seconds here cancel, and you're left with something that's going to be in meters? Okay? So doing the math here is not the problem. The problem is recognizing how you should express this number. Meaning, this number, when you do the math, is 6.49 times 10 to the minus 7. But the unit that we usually express waves in is nanometers. So do you guys remember what a nano of something is? Nano is 10 to the negative 9th, okay? So that means there's 1 billion nanos in something. Like if there, that means there's 1 billion nanometers in a meter. So that means, okay, if I had 1 meter, there would be 10 to the 9th nanometers. That's 1 billion, okay? And that would mean this would end up being 649 nanometers. Sometimes it's necessary to convert them to nanometers to compare them to other wavelengths, okay? So you will see this nano unit used a lot in this chapter, okay? Do you have any questions about that? Okay, so we'll hit that hard on Thursday, all right?